Hey everybody, we're starting to talk about two things today. Surface area is one new idea, and then volume is a second very different idea. If I give students a problem like the one shown here, here's a box, which we call formally a rectangular prism, because that's a more precise description of what this thing is. If I ask students to find the total surface area, many of them will multiply the length times the width times the height and come up with an answer that could not be more wrong. Okay. Finding the surface area is not a matter of length times width times height. You've probably all learned about length times width times height when it comes to boxes. That has nothing to do with surface area. So what is surface area? It's the combined areas of all of the distinct flat surfaces of the object, whether the object is a rectangular box or if it's more of a cylindrical box like a box of oatmeal, or if it's a pyramid or whatever it is. You add up the areas of all the distinct surfaces. Now, a rectangular prism or a box, a standard box, has got 6 surfaces to it, which I'm going to use this book to model. This book is basically in the shape of a box. It's got a front and a back, which is the same exact rectangular area as the front. It's got a top, which is congruent to the bottom, and it's got a left side and a right side, which are congruent to each other. So we've got to find the areas of all 6 of these surfaces and add them up. That's what is meant by surface area. Okay, so I'm going to calculate the area of the front surface here. That would be, this rectangle right here, which is 80 high and has a base of 50. And so that's 4,000, 80 times 50. But there's a back, which is congruent to the front. So if I double that 4,000, I'll get 8,000. I suppose I should write that in the place where I put an equal sign. 8,000 for the front and the back combined, right? Now I've got a top and a bottom. The top is how I'm describing that rectangle up there. All right, no dimensions are given up there, but they are given down here. These would have to be the same if it's a rectangular prism. So this is 12 by 50. And so that area is 12 times 50 is 600. But again, there's a bottom. So the two of those combined are 1,200, the top and the bottom. And then we've got a left side and a right side. And from our perspective of this thing, I would call that the right side. The left is the same. It's 12 units across like that, and it is 80 units tall because that length has got to be the same as this over here. So 80 tall by 12. That's 80 times 12 is 960. And again, there's a left and a right. So double that 1960 and you get 1920 for the area of the left and the right side. So the total surface area would be the 8,000 coming from the front and the back, the 1,200 coming from the top and the bottom, and the 1920 coming from the left and the right. And if I can do my arithmetic correctly and in a hurry, that would be 11,120. There are no units given with this problem. So let's just say units squared, because surface area is area, but it's just a number of areas all added together. And so the appropriate units for surface area is square units, whether it's square inches, centimeters, or whatever. Okay. Now this is an understanding approach, okay, to finding surface area. This is an explanation of how to find a surface area, a description of the process. There is a formula for surface areas of rectangular prisms, And I'm not actually going to include this in the notes that I'm posting. I'll jot it down here. You can look this up in a second if you just Google surface area rectangular prism. But the formula that I found when I Googled it looks like this. 2 times, and then in parentheses, length times width plus width times height plus length times height. Now let's make some sense out of that. Okay, if we call this the height of this rectangular prism and this the width, the 50 across from left to right, and let's call that the length of 12. All right, distributing this 2 gets us 2LW plus 2WH plus 2LH. All right, so this 2WH, here's the W and the H, that's the front face. But 2 times that front face because there's a front and a back. All right. How about 2 times the L times the W? Here's the L times the W gives us the bottom area, but there's the top that matches it. That's why we have 2 times LW and then 2 times LH. Now, what is the L times H? The L times the H would be the left and the right sides. Here's the L, here's the H. That gives you the right side, which is matched by the left. So there's the right and the left. So hopefully that makes some sense out of the formula. And you are welcome to use this formula on any homework problem, quiz, or test problem if I ask you to merely find the surface area of a rectangular prism. Notice I said the word merely find, which suggests that that's a pretty easy problem to do. It's going to be among the easiest problems for you to do, because really all you got to do is plug these numbers into the formula and crank out the answer. But you need to have an understanding of surface area in order to do any of the more difficult problems, like the one we're going to do on the very next page. Okay? You need to have an understanding. Surface area means find the areas of all the distinct individual surfaces and total them up. Now, a couple minutes ago, I heard myself use this word, and I hadn't explained it to you. Maybe you didn't even notice it, but I used the word face. Okay? That's kind of a shortcut for the word surface, okay, which has the word face in it. What we mean by a face of a three-dimensional object is one of the flat surfaces. Okay, so this would be a face of that rectangular prism, all right? And any of these other surfaces would all be faces. That's another face right there. Okay, so a face is a polygon shape. Well, not necessarily. It doesn't even have to be a polygon. It could be circular when we're talking about cylinders. But it is a distinct surface of a solid object. Okay? And you'll hear me use that word quite a bit. I don't want you to be puzzled by what I mean by that. Okay? Now, the second thing that we're talking about in this lesson is volume. Okay? And to calculate the volume of a rectangular prism, that's where you would use length times width times height, okay? And I think everybody's learned length times width times height, but you have to understand the difference between surface area and volume, okay? Let's imagine we had units for these measures, 12 centimeters, 50 centimeters, and 80 centimeters. Length times width times height then would not simply be 80 times 50 by 12. It would be 12 centimeters times 50 centimeters times 80 centimeters. The 12 times the 50 times the 80 would be 48,000. What are the units then associated with this volume? Centimeters times centimeters times centimeters. What is that? It's centimeters to the third power, right? Just like x times x times x is x cubed, 48,000 centimeters cubed, or cubic centimeters. The measure of any volume will always be in cubic units, not square units. That's one way of identifying a very important fundamental difference between surface area and volume. Surface area is flat surfaces, flat areas just all totaled up, square units. Volume is cubic units. It's not flat surfaces, it's how many cubes can fit in to this box here. Cubes that are 1 centimeter by 1 centimeter by 1 centimeter. 48,000 cubic centimeters means 48,000 of these. This is 1 cubic centimeter. Okay, because it's 1 times 1 times 1 is 1, centimeters times centimeters times centimeters, cubic centimeters. So theoretically, we could fit 48,000 of these inside this. Volume is three-dimensional stuff, okay? I'll use the word space, the interior space, when I'm talking about volume. Part of the trouble in talking about surface area and volume is sometimes I might also use the word space to refer to the interior of a flat object, okay? And I really work hard trying not to confuse you on that sort of thing. Okay, volume is three-dimensional, okay, whereas area is completely flat. And I think after some experience as a teacher, I can appreciate why sometimes students confuse the two, at least at the beginning, surface area and volume, because the surface area of this box exists in three dimensions. Not all of the surface area of this box is in one, what we would call plane, a geometric plane, which is a flat surface that extends forever, right? We've got some of the area in this plane that stands up, okay? And then we've got some of the area in this plane, which exists horizontally like this. So not all of the area is all in one plane. It's not all in two dimensions. The area exists in three dimensions, okay? But we're only calculating the area 2 dimensions at a time, okay? The volume is the stuff inside those surface areas. Okay. And so be clear on the distinction between those two. It's sort of like the distinction between circumference and area. The circumference is the length around the outside. Okay. But because that length is drawn in a circle, that length is not just a one-dimensional length now. Right? If you just draw a line, that's literally a one-dimensional object. It has no height to it, all right? But when you wrap that straight line in a curve, or when you wrap that line around here, now that length exists in 2 dimensions. It exists in the horizontal dimension and the vertical dimension. But when you're calculating perimeter, you only count like 1 dimension at a time. You add up the individual lengths, and the area is the stuff inside. Okay, so you must know the difference between surface area and volume. Okay, I will be very clear in any problem that I give you, whether I'm asking for surface area or I'm asking for volume. Oftentimes I will ask for both. Okay, but make sure you're answering the question that I'm asking. Make sure you understand the difference. Okay, I've written down here in the lower left corner a slightly different formula for the volume of a rectangular prism. That capital B stands for base area. It's distinct from a lowercase b, which we've always used to stand for a base edge, right, of a two-dimensional object. This capital B is capitalized, so we don't confuse it with a lowercase b. It stands for a base area. I was going to try to convince you why this is a better formula than length times width times height for rectangular prisms, but I I changed my mind. I don't believe it is a better formula. So I'm not going to try to convince you. Um, so we'll just kind of skip over that, although this is a formula we will begin using in the very next lesson for different types of three-dimensional objects. For the time being, let's just forget about that formula, okay? All right, as promised, a much more challenging problem on this page. I want us to find both the volume and the total surface area of this thing. I'm going to refer to it as a step stool because that's kind of what it looks like, although the first step is very, very short. Okay, let's call it a step stool. Now, you cannot just do a length times width times a height. What would you use for the length? What would you use for the width? What would you use for the height? There's a lot of numbers, a lot of measures in this thing. And this thing is not a simple rectangular prism. So that formula does not apply. What you've got to do is, remember when we were finding areas of shapes like this? And we talked about three strategies. Either cut that into two rectangles and add those two areas together. We've got a formula for rectangle areas. Or maybe cut it into rectangles that way and add those two areas together. And in either case, you might have to do a little extra work finding the correct dimensions of each of those two rectangles. Or a third option would be pretend you've got a solid rectangle like that, calculate that area, and then subtract the area of that upper right corner because that really shouldn't be included in the total, right? Three strategies there. Never matters to me what strategy you use. We have three very similar strategies for this three-dimensional object when it comes to finding the volume. One option would be to split this into two boxes by slicing through this step stool vertically right there so that we have a nice rectangular prism in front and we've got a taller rectangular prism in the back, and then add those two volumes together. Or we could slice it this way, extend that line all the way to the back. And now we've got a bottom rectangular prism that goes from the front all the way to the back. And then we've got a top rectangular prism, and we could add those two volumes together. Or our third option might be to imagine that this thing is not a step stool, but a solid rectangular prism, and find the volume of that entire thing and then subtract the volume of that space in the front top that we are imagining is there now, but it's not really there. So one volume minus another volume. And again, I don't necessarily think that any one of these three strategies are better or faster or easier than the other. It's just kind of, what do you instinctively or naturally see? How do you like to approach it? I'm going to do it this way. I'm going to do that first option, which is to slice it down through there. So I kind of have a front rectangular prism, which I will highlight here. Okay, there's the one. Now, what's the volume of that? Well, I got to find the length, width, and height of that. The width is 100. Okay. And by the way, length times width times height, all these three values are all being multiplied together. Does it matter what order you multiply them in? Right? 2 times 3 times 4 is the same as 4 times 3 times 2, or 3 times, doesn't matter what order you put them in. These terms, length, width, and height for rectangular prisms are really interchangeable, right? Because here, let me take this box here. Again, imagine this is a box. Okay, I know it's a book, but this is the height. We would say, oh, this is the height. Everybody would agree this is the height, right? And maybe we'd call this the width from side to side, right? And then the length would be like this length from front to back. But what if I just tilt this box over this way, right? Now this is the height, right? And I mean, really, if it's just a brown box, okay, without even a lid on it, just a solid box, and you really can't distinguish one side from the other. Like there really isn't a front. Like, I mean, there is a front of a book, but there's not really, is there really a front of a box when it's just a brown box? Right? So tilted this way and now this is the height, or tilted this way and now this is the height, right? They're interchangeable. So as long as I identify the proper lengths of the three different dimensions, it really doesn't matter what we call the length, what we call the width, and what we call the height. So 100 is one dimension. Let's see, 80 is not the length from the front to the back. 80 goes from this point A all the way back to this point B. But this box is not that long from front to back. Okay, it stops right there at point C. How are we going to find out how long AC is? We're going to need to find another measure in this diagram that is running parallel to that 80. Do you see any other segments in this diagram running parallel to the 80 and that have a measure alongside them? And you probably do. It's up there, right? That's running in the same direction as this 80. And it's a length of 22. So therefore that's 22. And therefore that is 22. And so we got to subtract that 22 from the 80. 80 minus 22, that's 58. That would be the length of that front rectangular prism from front to back. I'm going to put that in right there, 58. Okay, so that's another dimension. And then we need this dimension right here. We haven't been given that either, but that dimension is a vertical dimension. Can you find any vertical segments in this picture? Segments running parallel to those two that have lengths written alongside them? Well, sure. Here's a 40 and here's a 30. Okay. So if that's 30, that's 30. And then this little bottom vertical segment would be the 40 minus the 30. That would be 10 units there. So finally now, we have the dimensions of that front box. Okay, let me clean some of this up. Having sliced, let me put that slice back in. Having sliced this step stool this way, that front box there has dimensions of 158 and 10. So that's 58,000 cubic units for that front box. Now, the back box. What about this one here? What's the volume of that? Well, what are the dimensions of that? Let's see. One dimension, the vertical dimension is 40. How about the side-to-side dimension? Well, that's going to be the same as this right here. So that's 100. And then what is the third dimension? The third dimension would be here or here. That would be the same thing. So that's times 22. So 40 times 100 is 4,000 times 22 is 88,000. There's the volume of the back box. Add the 88,000 to the 58,000. And we get 146,000 units cubed. Okay, it's a volume, cubic units. All right. There's not a simpler, faster way to do this problem. Okay, I mean, maybe you could do it a little faster than I did because I'm explaining as I go, but really the process, there's no faster, simpler process than what I just did. Splitting the step stool by cutting into it horizontally that way, that's not going to make the process faster or easier, just slightly different. You're going to get two slightly different volume numbers. They're going to add up to the same total. Or, doing a giant box minus the top front part, not going to be a faster, easier process. Okay. Surface area now. There is no simple formula that you can use for the surface area, total surface area of this object either. Trust me, Uh, don't try looking one up. You're not going to find one. Okay. I want to clean some of this up again and leave the dimensions in that we figured out because we're going to need some of those dimensions to work through surface area. And I think I already erased one of them. This was 10. This is 58 from front to back. Any others? No, I guess. Yeah, those are the only two new lengths that we calculated. So surface area. All right, now, there's lots of different surfaces here. And what I'm going to model for you is what I want you to do. If you've got to turn in a quiz or a test problem to me and you've got an object like this, I want you not just to show your work, but to describe your work or label your work. In other words, don't just give me numbers, okay? I'm going to do this. I'm going to write front, okay? Remember, in the previous rectangular prism, I had a front and a back, which was congruent to the front, a top and a bottom, which was congruent to the top, and a left and a right, which was congruent to the left. So I'm going to take the same basic approach here. I'm going to start with the front and then do the back. Well, actually, here's the problem. Where's the front? What would you call the front? There's really two different front sides, aren't there? There's this front, and then there's this front. Okay, so there's two of those. So let's call one of them the lower front, and then let's call the other one the upper front. Okay, and the lower front is 100 by 10, so that's 1,000, and the upper front is 100 by 30, so that's 3,000. Okay. Now, what about the back? Okay. The back we kind of can't see here, right? It's around behind this step stool. It runs vertically just like the two front pieces do. It's one section, right? And it is 40 units tall by 100 units wide. 40 times 100. That's 4,000 for the back, and that's the whole back. Okay, so front and back, but the front comes in two pieces. Now let's do top and bottom, okay, just like I did on the front side. But again, the top is not just one piece. Think of this step stool, let's say, instead of being a small step stool, but being a very, very large industrial building. Let's say this is a picture of a really large, let's say, manufacturing plant or an office building or something like that. Okay, and the top would be like the ceiling or the roof of this building. Well, there's two sections of the roof, right? Now let me erase the front pieces. Here's one roof section, and here's the other roof section. Okay, so there's two tops. There's kind of, now how are we going to distinguish these two from each other? I'd call this like the forward top, and I would call this the rear top. That's how I would describe them. Okay, so the forward top would be, we figured this out, 58 by 100. 100 times 58, that's 5,800. Okay. And then there's the rear top, which is 22 by 100. Top, rear, that's 22 by 100. That's 2,200. Okay. Now, what's opposite the top? The bottom. Okay. The bottom we, again, kind of really can't see. It's underneath this whole thing. It's one rectangular surface that measures 80 from front to back and 100 from side to side, right? So the bottom, there's just one section of the bottom or the floor, and that would be 80 times 100 is equal to 8,000. Okay. Before we do the rest, and there still are two more surfaces, there's a left and a right here, I want to draw your attention again to the descriptions or the labels that I am including with my work. Okay. If you're going to do a problem like this in a quiz or a test, I need to see, and not just me, whether you got Ms. Rouser, Mr. Rusk, or me, we need to see, what these calculations that you're writing down, assuming you're even writing down the calculations, apply to. Okay. Because too often I get students who they've got a few numbers strewn all over the place, 100 times 60, 40 times 20, and then they've got an answer. And I don't know where they're applying this, where they're applying that. If you add up these totals, you don't get this. And then I'm left scratching my head going, how on earth did they get this total? I mean, and this is 6,000 right here, and this is 400 right here, and they come up with a total of 8,000. What did they do? Did they double this? If they did, why did they double this? Or did they triple it? Did they double that? Are they subtracting anything? It's stunning sometimes how incomplete and mysterious the work is that gets turned into me sometimes. And I can't follow it, and I give little to no credit for work that is not clear to follow. Okay. I will not assume that you know how to solve a problem like this. You got to show me all of the steps. And what I'm doing right here, labeling all of the surfaces and calculating them individually, that's how you can show me that you know what you're doing. Now, we still have a left and a right. Okay. Whoops. We got a left and a right. The left, we can see. All right. Let's get rid of all of those edges again. So the left is here. Now the left is not a nice rectangle like any of those other surfaces, but it's a combination of rectangles. It's an L, right? The left basically looks like this. Okay. And to find that area, we got to do what we did in the last unit, which is divide it into a couple of pieces, right? Maybe divide it this way, or you could divide it horizontally, or do a rectangle minus the rectangle in the upper right-hand corner. So that would be cutting it down like that, like I did earlier. And so this rectangle over here is 40 units tall by how long is that? Let's see, that was given to us earlier. That's 22. So 40 by 22. So that's 880. And then what is that rectangular area there? We figured out that's 58. We got that earlier. And that is 10. We got that earlier. 58 by 10. So 10 by 58. So that's 580. And so the total would be the 880 plus the 550, which would be 1,430 for the left. The right side, let's just go back up and take a look. The right side over here of this building or this step stool would be identical to the left side, right? So I'm not going to do all those calculations all over again. Just going to say that the right side is also equal to 1,430. Okay. Again, really not a simpler, faster process for finding the total surface area. Okay. No formula for total surface area. Really, we just used the rectangle formula for area over and over and over again. Okay. So what would the total be here? Well, we got 1,000 from the lower front. We got another 3,000 from the upper front. We got 4,000 from the back, which was all one piece. We got 5,800 from the forward top. We got 2,200 from the rear top or ceiling. We got 8,000 for the entire floor or the bottom. And then we got 1,430 for the left and 1,430 for the right. Total all that up, whatever it is. I'm not going to take the time to punch a bunch of numbers in a calculator, and I didn't work it out ahead of time. Okay. The answer is not nearly as important as the process. And we can all punch these numbers in and get an answer. Okay. There are two homework problems in the homework assignment. One of them is a solid object just like this, although I don't think you'd call it a step stool because the dimensions are quite different. It looks something more like that. I don't know if you'd call that a step stool. Okay, it's not really very wide, wouldn't be very sturdy to stand on, but it's essentially the same shape, very different dimensions, and you're going to have to find the surface area of that object and the volume. I mean, looking back on volume now, the volume was a lot less work, right? For complicated shapes, surface area is almost always a lot more work than volume. Okay. So you're going to have a step stool like object that you're going to have to find the surface area, and no shorter, simpler process than this. And then you're going to have another three-dimensional object I'm going to ask you to find the total surface area of. And it's not a step stool shape, and it's completely different. And there are 10 distinct surfaces. I mean, in this step stool, we had 8, 1, 2, 3, 4, 5, 6, 7, 8 distinct surfaces. In this last homework problem, there are 10. Okay. Now, a lot of the surfaces are congruent to each other. In that 10 surface object, you're going to have a lot more occurrences of this sort of thing, where once you find one surface, then you know immediately the area of another surface that is congruent to it. Okay. So that can shortcut the work a little bit, is by recognizing that. All right. That's it for the lesson today. So understand the difference between surface area, which is always measured in square units. It's totaling up lots of areas. It's a lot of work. Okay. And volume, which is three-dimensional stuff. It's the stuff inside, and it's always measured in cubic units. Okay. That'll do for today. We'll see you next time. Mm-hmm.